Let's try to solve this problem here. We have a red light of wavelength 633 nanometer from a helium neon laser passes through a slit of 350mm wide. So you see that this is a single slit problem because they say a slit. So this is a diffraction by a single slit problem. If you see two slits, then it's an interference by a double slit kind of situation. Okay, but this is single slit over here, and you use red light from helium neon laser. So helium neon laser is a typical laser that you see when we teach in classroom. That red laser, well, that's helium neon laser, and it produces light of around 633 nanometer. And now you're going to pass through this light through a slit of 0.350mm wide. The diffraction pattern is observed on the screen 3 meters away. Okay, so let's try to set up the scenario on through one diagram over here. Okay. So it's a single slit question, so you have one slit, and from the center, then you see your screen somewhere over here. Okay, so this is your slit, this is your screen. Okay, so what do you know? You know that the slit is 0.350mm wide. So this is A actually. A is 0.350 times 10 to the power negative 3 meter. And then the diffraction pattern is observed on the screen 3 meters away. So from the slit, go 3 meters to the right. That's where you find your screen. So this will be big D, the distance between the slit and the screen. Okay, you also have red light of 633 nanometers, so I'm going to represent it using a plane wave because that's what we have before it passed through the slit. Okay, I'm not going to overlap with the text over here, but this is the light that is shining onto the single slit. And if we look at its wavelength, the wavelength will be lambda is equal to 633 times 10 to the power of negative 9 meter. Okay, so this is the situation. They ask for the width of the central bright fringe and also the width of the first bright fringe on either side of the central one. So it can be the side above the central bright, it can be the side below the central bright, just one of it. Okay, so they don't need a lot of fringes. They want to analyze the center one and the next one. So let's draw its pattern. Okay, so it's always very you need to be very careful when you sketch the interference pattern and also the diffraction pattern, because the interference pattern and the diffraction patterns are quite different from each other. Okay, so let me sketch first, then afterwards we'll talk about it. Okay, so we'll start from somewhere around here, somewhere around here, somewhere around here. Okay, something like this. Okay, so how is it different from the interference pattern? If you look at the interference pattern, the brightness of all the bright fringes should be the same. But if you look at diffraction pattern, you can see that the central is always the brightest one. It has the highest intensity. But as you go to the next fringes above or below, you can see the next fringes, it gets dimmer and dimmer as you go further away from the central bright. Because what happened is the central bright over here is a result of constructive interference of all the secondary wavelets produced by the sources over here. So because it's a slit of finite wave, so you can think of it as many points as source of secondary Huygens wavelets. So there are many points here on the wavefront. So those many points, each point will be a source of secondary wavelets. So this region here will be overlapping many secondary Huygens wavelets. But because for the center bright fringe, the distance here, you always can find a pair that is constructive between all the points. So essentially what happens here is it's a constructive interference. You get a very bright fringe over here. But as you move on to the next fringes, those fringes on the side, what happens over here is not a complete kind of constructive interference. It's a partially constructive, partially destructive, some constructive, some destructive kind of interference. So the brightness will not be as bright as the bright fringes. And if you go further out from the central bright, here it's more destructive rather than constructive. there's plenty more pairs that are destructive compared to pairs that are constructive. So in that case, you see even dimmer kind of bright fringe. So the brightness of the dark fringe will decrease as you move away from the central bright. Okay, so that's the first characteristics that differentiate between diffraction and interference pattern. The second one will be the width of the central bright. Okay, the width over here, if you observe it and you compare it with the interference pattern, the width of the central bright for diffraction is thicker than the other fringes on the side. In fact, it is twice the thickness of the other fringes on the side. Okay, later we'll go through this calculation for A and B, which finds the width, and from there we can actually discuss deeper about it. So question A asks, what is the width of the central bright? Okay, so central bright will be this one, so we are looking for its width, which can be easily determined if you find here and here, and this will be the width of central. Okay, the second question asks for the width of the first bright fringe on either side of the central one. So either side can be the side above or it can be the side below. So let's say if you look at the side above, you want to know this width of this fringe over here. So I'm going to use another color. So this will be the width of the first bright. Okay, so W. Okay, so W1 or W2 or W0, well, we have to come back to the idea. For diffraction, right, your M cannot substitute 0. Okay, you have to go through the derivation video to understand why there's no 0 to be substituted for its M. But it has to start with positive negative 1, positive negative 2, positive negative 3, and so on. There's no 0 to be substituted, and we cannot label any M at the central bright. So the central bright over here, we are not going to substitute M is equal to 0. And if you are interested to know why, because the equation for bright is, the equation for dark is M lambda D over A. This is dark. Okay, for bright is Y is equals to M plus half lambda D over A. This is for bright. Okay, the issue is for diffraction, we start with analyzing the dark first. If you substitute M is equal to 0, you get Y is equal to 0. So Y is equal to 0 means that it's at the central. But is it a dark at the central? No, it is a bright at the central, right? So if it's a bright at the central, means that Y is equal to 0 is not valid to be called a dark fringe. So in that case, M is equal to 0 cannot be substituted. Because if you substitute 0, you get Y equals to 0, saying that Y is equal to 0 is a dark. But that's not the case. That means by M is equal to 0 is not valid for this equation. That's why you have to start with 1, 2, and 3. So now you know that for dark, this is 1, this is 2, this is 3. So you know that what's in between 1 and 2 will be 1.5. So 1.5 is 1 plus half, right? So that means here should be 1, here should be 2. Because between 2 and 3 is 2.5. 2.5 is 2 plus half. So this is 2. So the center one we will not label 0, we will not label anything. Because we technically cannot determine the position Y using any of this equation for the central bright. Central bright cannot be used. Both equations cannot be used to determine central bright over here. Okay, so that's the numbering for M over here. So we have known everything here. So this is the first bright. So we are going to call it as first order. So this is W1. Okay, so it's similar to the question that I discussed in interference pattern. So if you want to find the width, well, you find the distance from central to here first. So this is 1. So this is Y1 dark, not Y0, Y1 dark. And you know that from here downwards is also Y1 dark as well. So what can you say? You can say that for question A, W central is equals to 2 times of Y1. Okay, for question B, they want W1. What you can do is, okay, you can find the distance from central once again, but you find until you reach M is equal to 2 dark. So this is Y2 dark. Then if you find the difference between y2 dark and y1 dark, essentially that will be width of the first bright fringe. So for question B, you can find your width 1 by taking y2 dark minus y1 dark. Okay, so now it's just substitution. Okay, but let me manipulate the equation a little bit. 2 for dark, there's no plus half, so this will be 1 lambda d over a. So equation will be 2 lambda d over a. Okay, for question B, if you manipulate the equation, this will be 2 lambda d over a minus 1 lambda d over a. So the result of it will be lambda d over a. Why do I want to manipulate the equation? Because just by looking at this, we can see that width 1 is lambda d over a, width central is 2 lambda d over a. So the width of the central bright over here will be twice the width of all the other fringes. If let's say the width of this first bright fringe over here is 5 mm, then the width of the central bright will be 10 mm. You have to be twice of all the other fringes. Okay, the width of the central bright is twice the width of all the other bright fringes on both sides of the central bright. Okay, so now that we know this already, we can proceed with our substitution. Okay, so you have your 2 lambda is 633 times 10 to the power negative 9. Your distance between slit and screen is 3.00. Divide by the width of the slit. The width of the slit is 0.350 millimeter times 10 to the power negative 3. So calculate this, I believe you get an answer of, how much is it? .0109 meter. Whereas for width of width of the first bright, they do the similar substitution but without the 2 in front. So this will be 633 times 10 to the power negative 9. Distance between slit and screen is 3.00. Divide by the width of the slit is 0.350 times 10 to the power negative 3. So if you calculate it, you get half the value of width central, which is 5.43 times 10 to the power of negative 3 meter. Okay, so it's a similar question to the interference pattern question that we discussed in the section 4, okay, the interference of double slit question. But you can see that for the double slit question, the width of central and the width of the first bright, they have the same width because the width are consistently the same on both sides and the center of the fringe. The whole interference pattern, the width is consistent. But if you look at diffraction, the central one will be thicker, it will be twice the thickness compared to the other fringes on both sides of the central. Okay, so that's the main differences that we are trying to highlight through these two questions over here. So that's it for this question. Thank you very much.